Okay, so the problem we have today is to solve this ordinary differential equation with the method of power series. The method of power series consists of assuming a certain functional form of this y, and that functional form is a power series. So here we have the power series expansion, and it will consist of replacing this y with the power series and finding uh, the coefficient, the conditions on this coefficients that will solve this. Now I'm finding the first derivative is this, and here I left the index blank because I wanted to mention that once you expand this first term, we have that is of this form, right? When you take the derivative, this term becomes 0, and this is the first term. Therefore, we actually need to start at 1. Furthermore, if you put 0 here, you have a 1 over x, and which is not part of the power series. So that's why that is a 1. In a similar fashion, if the second derivative has this form, and it starts with a 2 because of similar reasons, so the first term of this will be 0. And it will be like this. Okay, now that we have the derivative, let's try to plug them in. So we have x, the second derivative, which would be, oh, let me put the series first. We have the series here, and the other term, which would consist of the normal power series expansion. This is equal to 0. Now, if we simplify, we have that this is x minus 1 because we multiply an x here. And now what we want is to find conditions on the coefficients. I know that's ugly, I'm sorry. But so we want to be able to make this term the same power. So now we would need to actually manipulate this index in a way that this is expressed in the same power of x. So the way we do that is, let's see, here I have it already written. You would go and say, what kind of index here, n, would I need to put in order for it to be just a number? So it'll be n prime plus 1, because if you plug it in there, it'll just be x prime. So if we use this substitution just on this term, we have that'll be n prime equals 1, n prime plus 1, n prime, a n prime plus 1, x n prime, plus, and then this term. Now, this is an arbitrary index that is not really related to this. So I called it n prime not to confuse you, but we could start calling it again n, or maybe just start calling this n prime. So that's what I'm gonna do. I'm gonna relabel n prime as n and try to join the two. But if you notice, the initial index is still not matching. So we need to take the first index out of this one, which would be n equals 1, an, xn. So the form doesn't change. I just took the first term out so that we could start now from 1, and this is the first term of this. And here I'm gonna make the replacement of n prime to n, just so that it's easier to read the whole thing together. So that's there. Sorry, it's kind of hard. I have a better written here. Here I hadn't made this substitution yet. So now we can join the two because we can, let's say, quote unquote, factor out the sum or join the two sums because we can add them term by term, like so. And we can factor out the xn. So it'll look something like this. Now, this term by term needs to be 0. For reasons that I'm not going to go over right now, because I want to make this short. But in essence, it's the independence of if you imagine this as a basis in linear algebra, they're independent, and therefore they need to be, all the coefficients need to be 0. So therefore, this needs to be 0. So now we get this as the condition coming out of here. So this needs to be 0. So that means that the term a sub n plus 1 needs to be equal to minus 2 over n plus 1 again. And these are the conditions that would solve the differential equation. Now, you might ask, we can further expand this so that it looks nicer. But you might ask, okay, well, I kind of need something else. And you wouldn't be wrong. So if you imagine starting out to find out which are the coefficients, a and let's say 1 equals minus 2, since I'm replacing n equals 0 here, so it'll be, sorry, I can't do that. It will need to be n equals 1 first, because it can't be 0 here. So it'll be n equals 1, 2, a 1. So this relates the a2 to the a1, and the a0 it just needs to be given by initial conditions because this is a differential equation at the end. Therefore, in order to solve and find all the terms, you actually need to give me initial conditions. And since it's a second order differential equation, you need 2 initial conditions in order to define all the rest of the terms. So yeah, that's pretty much it. I don't want this to make this more longer than it should, so I'm gonna end it there, and that should be pretty much the whole solution.